Well, good morning, everyone. We have heard a lot of very informative information today about the history of ethanol, about how ethanol is cleaning up our environment, cleaning up our air that we're breathing, which has all been really educational, great topics. And I'm really excited because our next speaker is going to talk about the improvements in corn ethanol and what we're doing to reduce carbon emissions. It's certainly a really important topic, a very timely topic right now. There's a lot of attention being paid on climate change, and ethanol has a big role in that, in reducing carbon emissions. And so I'm really excited for Geoff's slides. This issue for the National Farmers Union has long time been a very important issue for us. We are big proponents of a move to E30. We actually have two of our state presidents here, Doug Somke from South Dakota and Gary Werdish from Minnesota. So this issue really couldn't be more important to our organization. And so we really appreciate hearing from Geoff. And so with that, I'll get to it. Geoff Cooper is our next speaker. He is the president and CEO of the Renewable Fuels Association. Geoff is really a trailblazer and a leader in our renewable fuels industry, and I'm very proud that he is here to speak for the ethanol industry to talk about such an important topic. So thank you, Geoff. With that, I will turn it over to you.
Well, thank you very much, Ann, and thanks to all of you for the opportunity. When Ann asked if I would come talk about the latest and greatest developments in corn ethanol's carbon footprint, I eagerly said, of course I will. This is an issue that I have always been very passionate about and have been working on for 15 years. And unfortunately, there just continues to be a tremendous amount of misunderstanding, misinformation, old data, bad science around this entire issue. And so it remains a fight for us to try and get the sound science and fresh data and just good information in front of policymakers and regulators and other stakeholders. I think the questions at the end of the last session really speak to a lot of the kind of conventional wisdom around corn ethanol's life cycle and its impact. So I was hoping that she'd be able to stick around to hear this presentation, but I will catch up with her later. But again, I just kind of want to talk about the corn ethanol carbon life cycle. And I want to start at a very high view. This is actually a 30,000 kilometer high view, and just a fascinating study that came out a few years ago from the National Academies, where they developed a new technology, a new method for measuring photosynthetic activity using satellites. And what they found through this study and through this data, which was a bit of a surprise to them, is that the Midwest part of the United States during the growing season here in the U.S. Boasts more photosynthetic activity than any other region in the globe. And you can see that reflected in the bright pink that shows up there in the heartland of the U.S. So there's more carbon dioxide being sucked out of the atmosphere by that region of the country than anywhere else in the world during the North American or the Northern Hemisphere growing season. One other finding from this study that I thought was very interesting was specifically about the ability of corn plants to assimilate carbon dioxide from the atmosphere and quickly suck CO2 out of the atmosphere and sequester it in the grain and in the stalks and in the roots and in the soil. And really these scientists were pleading with the scientific community to do a better job of accounting for that ability of the corn plant to assimilate CO2 as they analyze sort of the life cycle impacts of corn-based products, but also the impacts of climate change on agricultural production in that region of the world. So a very fascinating study, very high-level view to start out with, and I would encourage you to take a look at this. NASA scientists were involved in this, and they actually have some really cool videos, too, that go along with some of the satellite analysis that they did. So when you take all that CO2 out of the air, and then you've got 90 million acres of corn actively pulling carbon dioxide out of the atmosphere, where does it end up? And again, this is a very simplified kind of cartoonish schematic of where that CO2 goes. And it's overly simplified, of course. But what you see when we use corn for ethanol specifically, which is about 5 billion bushels, or about a third of the crop produced annually, is that carbon that gets locked up in the corn kernel goes to the ethanol production facility, and in rough terms, about 1/3 of it leaves as CO2 emissions during fermentation. About 1/3 of that carbon becomes locked up or contained in the distiller's grains co-products that Steve Vandergren was talking about. That is fed to livestock and poultry and returns to the atmosphere. And then 1/3 ends up in the fuel, in the ethanol itself, and comes back out the tailpipe as CO2 when that fuel is combusted in an internal combustion engine. And then, this cycle continues, and the next crop of corn that's growing sucks up that same amount of CO2. So what we see with bioenergy, and really the benefit of bioenergy, is that we're recycling atmospheric carbon. And when you contrast that to what we do with fossil fuels, it's a very distinct difference. With fossil fuels, we're taking carbon that's been sequestered underground for hundreds of millions of years, been locked up, carbonaceous material deep underground, and we're making that into fuel. We're extracting the energy out of it, and then we're venting it into the atmosphere. It's a new emission. It's additive. With bioenergy, we don't see that. We are simply recycling CO2 that's already in the atmosphere. And believe it or not, this is a fairly simple concept, but there's a lot of misunderstanding about this cycle. You've got professors at University of Michigan, for instance, that pretend that last piece of this cycle isn't real or doesn't occur. So we spend a lot of time just re-educating people about this carbon cycle that you learn about, and photosynthesis, things you learn about in 7th or 8th grade science class. Now, of course, the question comes up, well, what about all the energy used in this process to take that corn and plant the seed in the ground, to harvest it, to fertilize it, to protect it from insect and other pressures? What about harvesting that grain and shipping it to the ethanol plant? What about the energy use at the ethanol facility, and then shipping that ethanol to the end user? All of those emissions, all of those life cycle emissions and energy use is really the subject of life cycle analysis, sort of cradle to grave analysis, and we do have very good tools and very well-tested methods of measuring these impacts. And so I'm going to talk about some of that. And this schematic just, again, at kind of a 101 level, shows some of those inputs at various stages of the ethanol production process. And in life cycle analysis, we typically use a functional unit called grams of CO2 equivalent per megajoule of energy. And really what we do is we sum up all of the energy used from beginning to the end of this process, and all of the emissions related to that energy use, and that's used to generate what we call a carbon intensity score, or a CI score. You'll see one input there into this process that's got an orange arrow and a question mark, and that's been the subject of a lot of debate, a lot of discussion, a lot of analysis over the last 10 or 15 years, and that's around this notion of land use change, and whether expanding our use of agricultural products for biofuels is somehow causing expansion of cropland into native grassland or into forest, and if we're chopping down forest to make room for biofuel crops, shouldn't those emissions be charged to the ethanol life cycle? They probably should if that was happening. But I'm going to show you some of the latest developments there. And again, this gets to some of the questions that were asked at the end of the last panel. But I want to start with, again, I think one of the reasons that there is such a lack of understanding about corn ethanol's current life cycle is because this is the last thing that a lot of people remember about corn ethanol's greenhouse gas impacts. Back around 2008, 2009, both the U.S. EPA and the California Air Resources Board were evaluating corn ethanol's life cycle greenhouse gas emissions. And they were doing so because they had brand new laws that they were writing regulations on and beginning to implement, and those laws required these agencies to evaluate the life cycle emissions of not just corn ethanol, but various other fuels as well. And it was a fairly new science in terms of broadening things beyond kind of that simple contained supply chain. EPA decided, well, we want to look at all the ripple effects of what happens if we increase demand for renewable fuels, and then CARB jumped in and said they wanted to do the same. But the initial analyses from both these agencies were incredibly flawed, based on really outdated information and data, based on using methodologies and tools that were not quite ready for prime time. And so what you ended up with is EPA said, look, our analysis shows that on average, corn ethanol reduces greenhouse gas emissions by 21%, but that doesn't happen until 2022. And so they baked in some assumptions about process improvements that would be needed to get you over that 20% level. And then at the same time, you had the Air Resources Board in California saying average corn ethanol doesn't reduce greenhouse gas emissions when you compare it to gasoline. They're about the same. And the bright green piece of these bars that you see for both analyses is that land use change emission estimate. And again, this is based on the notion that if we grow demand for corn ethanol, the Brazilians are going to have to chop down rainforest to plant more soybeans because there will be less acres for soybeans in the U.S. and all these ripple effects and kind of knock-on things are happening, and they use these economic models, partial equilibrium models, to estimate all these things, and this is where they ended up. So obviously, if this is the last time you checked in on corn ethanol's life cycle analysis, you've got some bad information and bad data. This is, this was bad when it came out, and it's really bad now. And of course, hindsight is always 20/20. Some would argue that those regulators were doing the best they could based on what was available. But here we are a decade later, and this is what we know today. We know that the real world data shows that those early estimates of land use change were grossly overstated. There has not been net expansion of cropland in the U.S. There's been no identifiable relationship between biofuel production and deforestation in the Amazon or Malaysia or anywhere else. And so when you look at those original estimates of land use change emissions, the first paper that came out, the first analysis that was kind of the nuclear bomb that dropped in this whole discussion was from Tim Searchinger at Princeton. And he came out with this cobbled together slapdash analysis and said the land use change emissions alone are over 100 grams per megajoule. And that doesn't even address all the process related kind of supply chain emissions. And just for reference, gasoline is around 95, 98 grams per megajoule. So he was saying just the land use change emissions alone make ethanol worse than gasoline. A year or two later, EPA and CARB came out with their estimates on land use change. They were about 30 grams per megajoule each. And more recently, around 2015, CARB revised its analysis and brought it down to 19, which we still think is far too high. Purdue University's got one of the economic models that was used by EPA and CARB both. So they've been continually updating their modeling, and they've recently came out with a 12 gram per megajoule number. But we think the most reputable and sound analysis of what is actually occurring in terms of land conversion that could possibly be tied to biofuel expansion has been done by the Department of Energy and Argonne National Laboratory, specifically in conjunction with some of the folks at Purdue. And their latest analysis shows, land use emissions, if they're occurring, are probably on the order of 4 to 7 grams per megajoule. We also know 10 years later that the agencies, EPA and CARB, both grossly overestimated emissions that happen in the rest of the supply chain as well. How much energy is being used at the ethanol plant? how much fertilizer is being put down by the farmer, what is the corn yield, what are the ethanol yields. 10 years later, we have a lot better data on that, and it shows that they were way off in their assumptions. And specifically on the question of land use, I want to just highlight quickly that chart on the left there. When Congress passed the Energy Independence and Security Act of 2007, which expanded the RFS-2, it included in the law specifically provisions that said if cropland in the U.S. expands beyond this baseline level in 2007, then that feedstock, any corn, soybeans, any feedstock that would come off those expanded acres would not qualify for RIN generation under the RFS if it was converted into biofuels. So there were provisions in the law that prohibited the expansion of cropland for the purposes of producing biofuels. And so what that chart shows is what that 2007 baseline level was. It was 402 million acres in the U.S. were engaged in crop production or some other kind of agricultural production. Each year, EPA is required to estimate agricultural land use relative to that baseline. And what you see there is each and every single year since 2007, that amount of agricultural land continues to trend downward. So we are well under the amount of cropland that was in production in 2007 when the RFS was expanded. The other chart that I'm showing here is sort of addresses one of the other myths that was popular around the 2007, 2008 timeframe, which is, what we do here in the U.S., if we expand our base of cropland, it's going to push soybeans and wheat and other crops to the margin, and other countries, other producers around the world are going to have to make up that marginal production that we lose here in the U.S. And so it's going to happen in Brazil, and what's going to happen is they're going to plow up their pastures, and they're going to plant soybeans, and the cows that were eating the grass on those pastures are going to be pushed into the rainforest, so they're going to cut the rainforest down and feed the cattle on new pastures in the rainforest. And so, through all these kind of convoluted reactions, the agencies were coming up with these land use change analysis and emissions estimates. What we've seen in the real world is deforestation rates in the Amazon have trended down significantly since 2004. Now, we don't have 2019 data yet. It's likely to show an increase, right, based on what's been going on in Brazil. But clearly that has nothing to do with our production of biofuels here in the U.S. I also want to look at what's been happening on the farm the last 10 or 20 years. And again, I wish the woman who asked the question at the last panel was here to see this. We are not expanding our use of fertilizers. These three plots show farmers' use of the three kind of key macronutrients that are used in corn production: nitrogen, potassium, and potash. And this is on a input per unit of output basis. And what we've seen is farmers have grown more efficient in their use of not only these fertilizers and macronutrients, but if I had charts that showed pesticide and herbicide application, it would show an even steeper downtrend. So farmers have become far more efficient in their resource use. And again, all of these products have greenhouse gas implications. And so when we're using less fertilizer, we are emitting less greenhouse gas emissions on the farm. This data, unfortunately, only runs through 2016. This is from USDA. When the 2018 data becomes available, we expect to see a continuation or an acceleration of this downward trend. Here's another way of looking at land use in the U.S. specifically for corn. The blue bars and the left axis there show millions of acres of corn planted in the U.S. And what you see there is all the way back to 1930, we haven't really expanded our acreage that is planted to corn. In fact, we're lower today than we were in the 1930s by 10 million acres or so. But if you look at the orange line and the other axis, that's how many bushels we're getting off of each acre of corn. And so you go back to 1929, 1930, we were getting about 25 bushels per acre. Today we're getting 175, 180 bushels per acre as a national average. States like Iowa, Illinois, you know, they're upset if their state average isn't 200 bushels per acre. And all of this has been achieved, at least in the last few decades, with reduced inputs per unit of output. So again, this is, I think, a fascinating story that we're not doing a good enough job of telling, quite obviously, when we still have questions about the sustainability and impacts of commercial corn production and what it means for the ethanol life cycle. We're seeing improvements at the ethanol plant as well, and I'm sure Jim Sire could speak to these quite well. This is just the last 5 years, and what this is looking at is BTUs per gallon. How much energy is the ethanol plant using per gallon of production for ethanol? And you go back to 2014, and it was about 28,000 BTUs per gallon. And I wish this chart went back to 2000 or the late 90s, because that number would have been double. It would have been around 45,000 BTUs per gallon. But again, just in the last 5 years, you've seen a reduction from 28,000 down to about 25,000. And these are real numbers. They come from an accounting firm out of the Twin Cities, Christensen and Associates, that has a benchmarking program that I think something like 80 ethanol plants belong to. So, you know, nearly half the industry is submitting its numbers every month and comparing their operations to their competitors. The green bar shows kind of the top quartile, the top 25%, and you can see their energy use is even far lower than the average. So when you take all of those improvements and add them together, what you get is a significant reduction in the overall life cycle greenhouse gas emissions associated with corn ethanol. Carol mentioned on the last panel that California, 10 years after they started the low carbon fuel standard, are realizing that, hey, this is a pretty good fuel when it comes to reducing carbon emissions. It's available at a low cost. And yes, it's not immediately changing California to full carbon neutrality, but it's doing a pretty darn good job of reducing emissions in that state. What this chart here shows is California's, this is data straight from the Air Resources Board. Every quarter they publish the average carbon intensity of the ethanol that was used in the state. And if you go back to one of the slides I showed earlier, they originally started out in 2009 saying ethanol is worse than gasoline or no better. We were able to convince them that by 2011, when this program began implementation, that ethanol is better than gasoline, and we showed them tons of data, lots of modeling, and they said, well, okay, it might be marginally better, 88.5 grams per megajoule compared to 96 for gasoline. So fine, we'll agree that corn ethanol gives you about an 8% reduction. And that was borne out as individual producers submitted their data and their natural gas receipts and the mileage that the ethanol was traveling to the state and everything else. But over time, you've seen that reduction fall dramatically. We've seen about a 33% reduction in the carbon intensity of ethanol consumed in California. And today, the Air Resources Board would tell you, yeah, ethanol in the third quarter of 2019 was reducing greenhouse gas emissions by more than 40% compared to California gasoline. And that still includes 19 grams of that 59 gram number is a land use change penalty that we still think is unjustified. So even with that bogey, we're still achieving a greater than 40% reduction in California. Also want to point out the orange line at the top, which is the comparator. That's gasoline. What's happened to the carbon intensity of gasoline in that same time? It's gotten worse, 5 or 6% worse, as the sources of crude oil that are being used to produce gasoline that's used in the state have gotten more carbon intensive and harder to extract. And in fact, again, you go back to 2009, 2010, I remember going to some of the hearings where members of the Air Resources Board said, we just don't see much of a role for corn ethanol in this program. Well, here we are a decade later, And ethanol is responsible for about 40% of the greenhouse gas reductions achieved under that program since its beginning in 2011. That's more than any other low-carbon fuel. It's 4 times more than electricity. And if you're just focusing on the gasoline side of the equation, just the gasoline pool, ethanol is responsible for about 85% of the reductions achieved in the gasoline pool. So times have changed, but we have a lot more work to do, and we think we have a lot more room for improvement in the corn ethanol life cycle. I want to go back to this little cartoon that shows about 1/3 of that carbon that corn, those corn acres were sucking out of the atmosphere, returns to the atmosphere through fermentation at the ethanol plant. What if we were to capture that CO2? What if we were to sequester that CO2 or use it for enhanced oil recovery? Significant benefits could come from that. Today we've got, maybe 2 out of every 10 ethanol plants is capturing some of that CO2 and selling it into the beverage, bottling industry or food service or other places where CO2 is used. Very little of the CO2 coming from fermentation today is being sequestered underground, although that's changing. Just within the last few months, Red Trail Energy in North Dakota they are doing carbon capture and sequestration, and they have applied for a pathway in California. The Air Resources Board is looking at it. If CARB approves it, what they're going to see is a reduction in their CI score from about 75 grams per megajoule down to about 35 grams per megajoule. So capturing and sequestering the CO2 from fermentation could result in about a 40 gram per megajoule improvement in the ethanol CI score. But I want to start with the CO2 uptake by the corn itself. It was mentioned on the last panel that corn producers today have made remarkable improvements in how they're managing agricultural soils, and so much of the CO2 that those plants are pulling out of the atmosphere is in fact being sequestered in the ground, especially when you look at tillage systems like no-till or other conservation tillage methods. The root masses have gotten so much bigger. The disruption of the soil has been minimized. Farmers are not getting credit for that sequestration that's occurring today. They should be getting credit for it. We're working with regulatory agencies on ways to do that. But there again is probably another 20 or 25 grams per megajoule that is being left on the table, and would see even further adoption of these practices if farmers were incentivized to adopt them. So I just want to finish with a few slides based on, this one's based on some modeling that we did at RFA that shows, and this is actually a year old, but it shows kind of the average kind of typical corn ethanol today, would be about a 57 gram per megajoule number if you're using the Argonne GREET model, and that's about a 40 to 45% reduction versus gasoline. Again, that's a big reduction. That's something we should be proud of. But we think within the next 3 to 5 years, due only to improvements on the farm and at the ethanol plant, and technologies we know are being adopted today by ethanol producers, technologies that are being adopted on farm, that reduction, that the carbon footprint will continue to shrink. And we expect in the next 3 to 5 years, the average gallon of ethanol is going to achieve a 50 to 60% reduction versus gasoline. But longer term, if we have the right policy incentives in place, the right regulations in place, and just the right signals being sent, we think that corn ethanol can truly approach carbon neutrality, even when all the energy inputs and emissions are summed together. If we're adopting carbon capture and sequestration technology, if we're fully crediting the soil carbon sequestration that's happening, we think that offsets or more than offsets the emissions related to natural gas consumption at the ethanol plant, emissions from fertilizer production and application and other phases of the life cycle. So I showed this slide around a few times last year, and people said, oh man, that, yeah, that sounds great, looks real nice, but we'll believe it when we see it. So I was really pleased when a few weeks ago at another meeting I was at, some modeling work that I was completely unaware of was presented and basically found the same thing. And this came from the Great Plains Institute. They're an NGO out of the Twin Cities. And they basically said, if you start on the left with sort of the GREET default kind of average corn ethanol today, you've got a 55 gram per megajoule number. Again, 45% reduction versus gasoline. But as you work across to the right and you assume the adoption of some of these other technologies, you can get to carbon neutral or carbon negative corn ethanol. And the green bar you see on the end there where you're actually providing a 34 gram per megajoule carbon, benefit, it assumes that the ethanol plant is using renewable natural gas. You heard Steve Vandergren talk about the facility in Kansas. It's using wood waste to generate its thermal energy needs. So there you go. But it also has carbon management and carbon capture and sequestration. So, in theory, if an ethanol plant is using that suite of technologies, it could be achieving a negative carbon score. And you put that ethanol in an FFV or a flex fuel hybrid, it's going to do every bit as good or better than an electric vehicle. So this is just the final slide, and I just wanted, this is probably hard to interpret, so you may want to study it a little more carefully when the slides are sent around. But what this shows is just the carbon intensity number across the bottom axis, and what that should result in terms of a premium price for the ethanol at varying carbon values in the California market. And so focus on the yellow line at the top, because that's really where carbon prices are in California today. That's $200 per metric ton. So, for example, if you have a CI score of 65, you go up to where that yellow line is, and that should result in a 25 or 30 cent per gallon premium for your ethanol. That's a nice premium to get if you're an ethanol producer. You can take that and reinvest it in more technologies, cleaner technologies to take that CI score down further. Now, I will tell you, and ethanol producers would certainly tell you, they're not seeing that full benefit today in the California marketplace. And the reason for that is the market is flooded with this sort of low CI corn ethanol. There's more supply than there is demand for in the state of California, and that's because they have a 10% cap on the amount of ethanol that can be blended with gasoline. You boost that to 15% or 30%, you're going to see that value trickle back upstream to the ethanol producer. The other thing I would just point out real quickly while we're talking about this is, where do you think E85 sales are growing most rapidly? It isn't Iowa, it isn't Minnesota, it's in California. And it's just going like gangbusters out there because of this equation, because of the value that comes from the carbon intensity reduction. Putting a monetary value on carbon reduction has absolutely incentivized and encouraged innovation in the retail space in California, but also innovation in the production of these fuels. The other box I have here is just corn fiber ethanol, and we have an increasing number of member companies that are taking the cellulosic fiber that's in the corn kernel, and rather than passing it through to the animal feed co-product, they're converting it into ethanol, into cellulosic ethanol. And it has a very low carbon intensity score, somewhere in the 30s. There was 19 million gallons of this product recorded in CARB's last data release, so it is happening. And again, you can see the sort of economic premium associated with that level of low CI ethanol. So, LCFS was brought up in the last session, and I just wanted to point out that it has been, after fits and starts at the beginning with California, it has been an important policy for our industry and one that we today support. even though there are further improvements that we think need to be made to how they do CI scoring and life cycle analysis. So that's really it. I just dropped a lot of data and information and, charts and slides on you, but happy to address any questions, any comments that you have, or Ann, I don't know how you want to, what direction you want to take this.
I think we have, thank you. I know we're running up against lunch, but I think we do have time maybe for a question or two. Just a real quick comment. This is a phenomenal presentation, and I've seen parts of this before because RFA and the National Farmers Union is working with different groups to try to really educate them. We recently went to an event with the Carbon Capture Coalition and presented in front of a bunch of environmental groups and labor unions and entrepreneurs and even refining interests. And people were really blown away because they had no idea all these things had changed. So I think it really underscores the importance of events like today and all the rest of the speaking engagements that we're doing to try to publicize that. So just an editorial thank you. That was phenomenal. Dave, I saw you had a question.
Thanks, Geoff. It was outstanding. I see we're on the CI scores in the LCAs, the life cycle analyses. Everything is compared against gasoline per se. As you well know, the aromatics component of gasoline, EPA itself admits is at least 25% more carbon intensive. Other data shows much higher. Have you ever talked to folks, even at the CARB folks, about having the comparison, if we get especially to the point where we're substituting for aromatics, where they're comparing to that more carbon-intensive component?
That's a great question, Dave. I mean, and we have said from the beginning, we need to be comparing ethanol to what it's replacing. And it's not just gasoline, right? It's aromatic hydrocarbons and other octane sources. There has been some interest in looking more carefully at those sorts of comparisons. Argonne National Lab, in one of their iterations of the GREET model, did in fact do that sort of analysis where they're comparing ethanol as an octane source to other competing octane sources on a life cycle basis, and did find exactly what you're talking about: additional carbon savings, compared to other to other octanes versus just looking at gasoline. But that's an area of life cycle analysis and just this field that needs more work and more resolution. The other thing we've said is we need to be, in California and other places, if you're going to compare us to gasoline, you can't compare us to the national average gasoline. You need to compare us to the sources that are being used in that jurisdiction. We know, that there are varying degrees of carbon intensity when we talk about crude oil sources as well. So lots of work to do in terms of establishing the right baseline and frame for comparison.
Two quick questions, Geoff. One on the CO2 recovery from a plant. You said there's certain plants that are doing that. And you mentioned oil recovery. I know in the past it was hydroponics and greenhouse, growing tomatoes and whatnot. But just refresh me, wasn't there a tax incentive if the CO2, was it general for capturing CO2 or specifically if it was used for oil extraction? But wasn't there some legislation?
Yeah, the 45Q tax credit that came through, a year and a half or 2 years ago, it provides a substantial benefit. It's $35 a ton for sequestration or EOR, which, you put that sort of incentive on the table, and it really causes ethanol producers to take a hard look at whether, they should move forward with that capital investment. It's not inexpensive to set up a CCS type of system with an ethanol plant, and it, today it really only works in certain geographies and in certain situations. ADM in the middle of Illinois is another place that's got a perfect geological formation sitting underneath it to do this sort of sequestration. But having that tax credit available, and the final rules are still being written on how that's going to work, but that's a key piece of this.
One more quick one. On the E85 in California, well aware of how ethanol is such a turn from decades past when they hated ethanol. People may not be aware that E85 is classified as anything as low as 51%. Is that based on the production from the plant? How are they gauging that? Because that's a big difference whether you're actually at 85 or 51.
Yeah, well, in California, they don't adopt the ASTM specification for E85. They have a much tighter range to define what E85 is, and I believe it's 70 to 85% ethanol in California. But the data from CARB has shown, because they go out and measure and do sampling, and they've shown that E85 in California typically is E85. It's normally between 80 and 85% ethanol.
Sorry, everyone. We have time for one more question, and then we're going to go ahead and break to lunch, okay?
Well, it's probably more of a comment than a question, but I really wanted to build on what you and Dave Hallberg were talking about, not just looking at aromatics, but octane, as an octane credit. In our North Carolina study, 1 gallon of ethanol makes over 6 gallons of E25 at a 5% reduction per gallon. So I think when you look at an efficiency credit, it's a very nice story to tell what you're saying.
That's a good point, Steve, and the study from Argonne does look at the fact that, hey, if we're using ethanol as the octane source instead of aromatics or stuff coming out of the refinery, then they're running their reformers less severely, they're using less energy in the refinery, and that should, that's a credit that should go to ethanol. So there are all these very complex effects and indirect things happening that we just need to keep looking at.
I want to go to a different question, and I want you to jump in on this too. We talk a lot about E30, and obviously we're using a lot of cropland to produce E10 or E10 plus. Over what period of time could you imagine a transition in corn production to E30, and what would be the impact on U.S. land use?
We have done that sort of modeling, and we have, arrived at the conclusion that we could certainly support, our agricultural system could certainly support a 25 or 30% blend in the future. I mean, and one of the kind of important variables in that is the increases in fuel economy are going to reduce overall gasoline consumption. So, 25% of the gasoline pool, by the time you could actually achieve that, is much less ethanol than it would be today if you were to do it. But at the same time, you've got to look at the trend lines for crop yields. You've got to look at these other improvements in efficiency that we know are coming. I used to work at the National Corn Growers Association, and every year they had a corn yield contest. And the winners of that contest, had yields of 350, 400 bushels per acre. Our national average today is less than half of that. So are you going to have that sort of productivity across the U.S.? No. But it shows the potential of where crop yields can go. I mean, we've had honestly, the situation has been the reverse of what a lot of people think. We've had huge surpluses that have burdened our agricultural economy, burdened our commodity markets, and we think because of increases in productivity, we're going to have that again unless we have somewhere, some market for that grain, and we think ethanol is where it ought to go.
Is this too much of a stretch? Do you think that the corn industry could commit to meeting the demand for increased ethanol without increasing the corn acreage?
I think in certain scenarios that is plausible. That is absolutely possible. Again, it depends on the time frame and lots of other assumptions. But and I know the corn growers have done that sort of modeling too.
Just to add quickly, I know we're going to hear a little bit more on E30 this afternoon with one of our panel discussions. But just on behalf of farmers, I mean, if we're given a goal, we're ready to meet it. Our corn prices have been incredibly low, and we're looking for additional markets for it. We've done extensive research. E30 is widely used, and so we're looking for that kind of acceptance and that nationwide use, and that's something we're going to be spending a lot of time on.
And I'm sorry, I know you're supposed to be going to lunch, but just Ann made me think of one more thing. And that was when I was at the corn growers back in 2000, this would have been 5 or 6, we sat down with our board for a strategic planning session to talk about, how much ethanol could we make from corn in the near term, and came up with this strategic plan that was 15 by 15 by 15. 15 billion gallons of corn ethanol, production of 15 billion bushels by the year 2015. And as we kind of shop that around, people said, you're nuts. There's no way you're going to get there without vastly expanding cropland and having all these negative impacts. Well, guess what? We got there. We got there and surpassed it. We'll produce 16 billion gallons of ethanol this year. The corn crops have been, 15 billion bushels or higher. So Ann's right. When you put that vision out there and send the right signals, the marketplace is absolutely going to respond.